Assalamu alaikum. Today we will discuss Article 27.5, that is superconductors. What is a superconductor, and when it was discovered, what are the prospects of superconductor. So it's a generalized sort of an article, and we will know different properties of superconductors in it. When superconductor was discovered by a Dutch physicist named Camille Ons, he actually discovered liquid helium, and then he poured this liquid helium onto different substances, and while doing so he used mercury, and when he poured liquid helium onto mercury, he found out that after pouring liquid helium onto the mercury, the resistivity of liquid helium goes to decreases drastically, and in doing so the resistance becomes zero. And by showing this result he won a Nobel Prize. Then after some time, there were two scientists, Muller and Bednorz. They discovered that certain alloys can be made superconductors at temperature as high as 35 K. Actually, when Chameleons worked on mercury and showed that at 4K, he can convert different metals into superconductors. It was considered at that time that whenever we want to convert something into superconductors, the temperature has to be as low as 4K. But then these two scientists, they discovered that if they have alloys, and they can convert these alloys into superconductors even at high temperature, that is 35K. Whereas theoretician earlier had proven that it was impossible to ever get superconductivity. So, but they experimentally proved that some of the alloys, they show zero resistance at 35 Kelvin. It was such a tremendous achievement for these two scientists that they got again Nobel Prize within a year. So this is something very rare to happen, that after conducting experiments and showing results, and within a year the results are so superb that it's been accepted for Nobel Prize. Nowadays, alloys can be made superconductor at temperature as high as 135 Kelvin. And nowadays, instead of using liquid helium, in most of the cases, liquid nitrogen is used to make different alloys as superconductors. How these superconductors can be useful. Now, suppose that if a power line is made up of superconductor, then there will be no power loss. But obviously, to make a power line, a superconductor conducting power line, we have to maintain the temperature of the line throughout the city, and that will be quite expensive to do so. But in principle, if one suppose that we have a power line, you can transport electric energy without any loss, and if the resistance of the material is zero, then obviously the current will flow through the power line at very high speed, and as a result there will be magnetic field which will be very strong. So we have to counter the magnetic field as well, to cause any damage to the power line. So no electric field in superconductor. This is another important point, that no electric field exists in a superconductor because there were an electric field in the superconductor, meaning that there will be certain potential over the conductor. So if we have a certain potential in a superconductor, and we know that resistance in a superconductor is equals to 0. So if something if a certain value of V is there, and we divide that value with 0, we get infinite current. So we cannot have an electric field in a superconductor. So this is the reason that we cannot have electric field in a superconductor, because if we have an electric field, which means that there will be a potential difference. This will make the current up to infinity. If superconducting material is approached with a magnet, suppose we have this disk as a superconducting material, and we approach this disk with a magnet, then if we remember Faraday's law, and we will be studying Faraday's law in next chapter, or maybe uh, in chapter 30th, I think. Faraday's law is basically with rate of change of magnetic flux, we can induce EMF. So if we are approaching this superconductor with this magnet, so basically the magnetic flux is changing, and if the magnetic flux is changing, it will induce EMF into the superconductor. But we have shown earlier that that EMF, which is basically the potential difference, must be equal to 0. Otherwise, we get infinite I. So, but Faraday law says that if the magnetic flux is changing, then EMF must be induced. So, what happens actually is, a huge current can be attained inside a superconductor, but no EMF. So as we bring the magnet close to the conductor, eddy currents are going to run inside the superconductor. We will also study eddy currents in the next chapters, so I won't go into details over here, but just remember that these currents, they generate themselves in a conductor, and they are considered to be as negative currents. So when we approach the magnet, when the superconductor is being approached by the magnet, these eddy currents, they start running inside the superconductor, and the flux is changing, and these eddy currents basically, they will make this change in flux equals to 0. So if the flux is in this direction, then the eddy currents, if they are moving inside the conductor, they will produce a magnetic field which will oppose the field of the magnet approaching the conductor. So there will be no magnetic flux when the magnet is very far away. So there can be no change, and when this flux approaches the conductor, then the eddy currents, they will oppose it. So let's look at this figure. This is the superconductor. This is the magnet which is approaching this superconductor. When it comes near to the superconductor, what will happen, that eddy currents, they will oppose the field produced by the magnet, and in doing so the field will deviate from its path, and will move in this direction. So this will become a pressure region now. That is, the north pole of this magnet is being repelled by the field which is produced by the eddy current. This means that the magnetic field produced by the eddy current has the north pole in the vertical direction, that is towards the north pole of the magnet. So it will oppose it and will not allow the EMF to be induced in the superconductor. So the figure shows the superposition of the two fields, then effectively comes down to the fact that this is magnetic field. This magnetic field is completely repelled by the magnetic field produced by the eddy current, and we get a squeezed field. So here in this region we have a squeezed field. When there is squeezed magnetic field, there is magnetic pressure as north repels north. So what we can do that maybe we try to change the pole of the magnet and dodge the eddy current, but the instant we change the direction of the magnet, immediately at that very instant the eddy current will flow in the reverse direction, and the north there fields north south pole will be in the direction of the south pole of the magnet, because we have changed the direction of the magnet, and it will again repel the magnetic field produced by the magnet. So uh, in practical application, if we consider the practical application of the superconductor, we can use them in magnetically levitated trains, and if we have magnetically levitated trains, then the speed of the train will be very high, and there will be less frictional losses, because there will be no moving parts that are rubbing one another. So the movement of the train will be very high, and energy losses will be very low. Now, temperature below which the resistance of the material decreases to zero is called the critical temperature. It is denoted by Tc. There are two kinds of superconductors: ceramic with high critical temperature and metals. A lot of effort is being put in to find a superconductor at room temperature. Once we get hold on this technology at room temperature, its results will be tremendous. So not all the good conductors are superconductors. For example, gold, silver, and copper, they prove themselves to be good conductors, but they are not used as superconductors. So the graph below shows temperature versus resistance for mercury. Now the moment mercury reaches 0.42 Kelvin, that is the critical temperature, you see that in a very short time the resistance of mercury becomes zero, and we get a superconductor over here.